For the next little bit, we're going to talk about VPNs. VPNs, virtual private networks, and they're different from real private networks. Real private networks are leased lines. Virtual private networks are encrypted connections through a public network. And encryption is what makes it private. And keeping in mind that eventually anything that's encrypted can be decrypted. Eventually, if it's worthwhile, it can be hacked and cracked if we have those things set up. So VPN, a set of security protocols that are implemented on both ends of an insecure network to provide secure connectivity to remote partner sites. Before we start, we always draw these really cool tunnels that we send our encrypted traffic. And that's really good, but keep in mind that those really cool tunnels don't really exist. So we always draw these tunnels, and we say that, and I will too, that the traffic goes into the tunnel and then it comes out of the tunnel. What we're really doing when we put it in the tunnel right here is we're encrypting it, and when we take it out of the tunnel here, we're decrypting it so that the back side here, the unencrypted network, can now be able to read the traffic. So we're sending an encrypted information, and the type of encryption, the type of configuration that we use is what is going to dictate the security level of our VPNs. But it is because you got to remember that between here and there, you got however many routers that don't have any idea how to read an encrypted password. So we're going to have something decrypted or something plain text on it in order for it to get from point A to point B. And that's why I took the tunnels, and I'll draw the tunnels too, but it's not really a tunnel. It's an encrypted transmission when we do these things. Packets are kept private through encryption, other security mechanisms, authenticating headers, so that we know who we're talking to, and encryption. We can do one or the other, or we can do both with these things. It's always handy to have mutual authentication when you're sending a secure connection from one place to the other. Even if the data is sent over the internet, we can use these things. Internet, certainly not a secure place to be. The features for this thing, what we're trying to do here is prevent a man-in-the-middle attack. The best antidote to a man-in-the-middle attack is going to be encryption. Again, I always talk about these labs I used to do because I can't enable anymore. It doesn't work with Windows 10. But we used to do a man-in-the-middle attack, and we would use an ARP spoofing. It would, and this was all on virtual machines in the classroom. But you send your IP address and specify it as the MAC address of your IP address, your MAC address, and specify it as the IP address of the default gateway, so that the default gateway traffic goes to you. We did that. We would do that, and then we'll go to say, okay, now go to your email, which is encrypted, and you get a pop-up that says, hey, will you accept my certificate? And this is where it comes in to know what the certificates are for, and when you should get a pop-up, and that if you get a pop-up, the reason is something's wrong. And somebody actually said, okay, I'll take it. So when that happens, you've now lost your encrypted connection. But man-in-the-middle attack, one of the best ways to prevent a man-in-the-middle attack is through encryption, because they're not going to be able to read the information. Man-in-the-middle attack on the internet, from being able to read, copy, or replay the transmitted data, and poses a legitimate user, the confidentiality. Verify that the VPN packet originated from a legitimate source. This is where we're going to use authenticating headers, certificates, so that we're going to use mutual authentication. Each side can, may, doesn't have to, but probably should, can authenticate to the other side. So mutual authentication. Both sides now know that they're connected to the device that they expected to be connected to. And then verify that the packet is intact and not changed during transit. We're going to have some sort of a hashing algorithm to use with these things. the VPN, IPsec, all of the things that we're going to use is a framework. Prevent the man-in-the-middle attack. What kind of confidentiality are we going to use? What encrypting algorithms are we going to use? What encrypting protocols? And what if the other guy doesn't have that particular protocol? We're going to have suites of these things to where we specify a number of protocols and negotiate the most secure of them. And then authenticating headers. We're going to have certificates so that we can authenticate one to the other. And then what kind of a hashing algorithm are we going to use? VPN, faster, cheaper compared to the WAN options. Lease lines, one of the options. The other one, if you think about VPNs, let's think about the work-at-home user, or the traveling salesman user, or the Saturday morning network administrator having his second cup of coffee. All of these can conduct business across the internet. We don't want to do it unencrypted because, as you know, it's a dangerous place. People are constantly looking for information. VPN, faster and cheaper. What the salesman used to have to do is to dial up to a modem bank, which meant that the network administrator, the company, had to maintain a modem bank for users to dial into to do their updates. Why would they do that? They're out on maybe a 2 or 3 week sales jaunt, and you know, they've sold a bunch of stuff, so they want to get the manufacturing going. They want to get the orders in, so they go back to the company and update the database so that, yes, we can ship them, we can make them, we can do whatever we need to do with them. But communication becomes a really big deal with these guys. You sitting at home having your second cup of coffee, and the boss calls up and I just got locked out and I forgot my password and I need you to fix it because I have a very important presentation to give in an hour. What are you going to do? Are you going to just telnet? Don't want to do that because it's not a very secure protocol. We want to go via a VPN of some sort in order to get their virtual private network. And there are a number of clients. The other is available worldwide. The dial-up, if you were in Europe, the dial-up, all the everything, the power, all the everything is going to be a little different than it is in the U.S. Or if you go to Japan, it's going to be different. But the internet is going to be available to us worldwide on our laptops or whatever device, laptops, phones, tablets, whatever device that we're using to get there. VPN Components is an internet VPN. The internet, and then the lines here again that we're showing is these nice, neat, well-constructed tunnels or direct connections. Keep in mind that as you go across that internet, there may be 5, 10, 15, 20, 30 routers involved in this. So the communication may go through a lot of devices at a lot of different locations when we have those. The VPN tunnel, again, from one location to the other location, the nice tunnel here, but again, I keep saying it's not an actual direct connection. It's going to go through the different devices that are on the internet. Encryption and authentication. And the answer is maybe. We don't have to do both. We may have a situation that we only want to be sure that we're authenticated from one to the other, that the communication doesn't have to be encrypted. Encryption and authentication is going to slow things down. Anytime we do this, it's got to be processed, which means it's going to take CPU cycles, which means it's going to slow things down a little bit. So how much of a load can we want to put on the devices? Encapsulation, and hopefully we've talked about it a little bit. Encapsulation is the process of enclosing a piece of data into something else, into a larger piece of data. And well, we'll have some images here, but let me make my bad drawing here. What we would have, going into the tunnel, we would have our data packet back here, which would have its all of its stuff. It's going to have its MAC and its IP and the data and TCP and all the other stuff. So what we would do is if we encrypt this data, encryption, if we increase this IP address, the IP address, if it gets encrypted, these routers aren't going to be able to read it. So what we will do is to encrypt the whole data packet or encapsulate it, and on the outside we're going to put an unencrypted IP address so that we have our encrypted data back here, our protected data, and on the outside we have an unencrypted address so that it can go through those routers. And the encapsulations are things that we've been looking at in Wireshark. The header, the data header, the transport segment, we have the TCP header, and then we have the IP header, and then we'll have the header information, the MAC header, or whatever layer 2, let's say layer 2 header, whatever layer 2 information we're looking at. When we do the layer 2, all of this other information here is going to be enclosed in it, including the IP address. We can now put another header on the outside of this and encapsulate the entire data packet and send it from one location to the other location. And when it gets there, it gets decrypted, the header gets stripped off and decrypted and then sent to the wherever it needs to go. IPsec is one of the methods that we can use to do this. We can, there's another one, generic router encapsulation, a GRE encapsulation, that just encapsulates. We have to add everything to it. And we do the same thing with IPsec. The main goals: confidentiality, integrity, authentication, and anti-replay. Anti-replay keeps showing up more and more and more. It's a layer 3 protocol, a framework of open standards, algorithm. The framework of open standards is which encryption protocols are we going to use? We're going to use AES. What if we use AES and the other end can't do it? Then we may have to include also AES or DES so that the devices do a negotiation process to determine what's the most secure protocol that's available on both of them. Data integrity, what hashing algorithm are we going to use? Authentication, how are we going to do that? And then anti-replay. A number of ways to do anti-replay, timestamp being one of the things that we can do with it. Framework of open standards here, IPsec, can be algorithm independent. The Internet Key Exchange, the IKE, establishes the shared security policy and authenticated key. It does the Internet Security Association Key Management Protocol, ISACAMP, specifies the mechanics of the key exchange. There are several different ones to do that. One of them, and I don't have a slide in here, but one of them is the Diffie-Hellman, and it is based upon division of numbers. Each side thinks of or uses a random number, and then we do some mathematical operations to it, encrypt it with the other user's public key, they encrypt it with my public key, we get their number, and then we do some more mathematics, and eventually they match. So eventually the keys are going to match after we get through doing that. But the issue is the key exchange. We need to keep the key exchange secure. If it gets compromised, then we have issues, obviously, with that. Authentication header, authentication only, IP headers and payrolls. It has no payloads, not payrolls. Provides authentication and data integrity, and it does not provide confidentiality. There's no encryption with, or no confidentiality, no encryption with authenticating headers. Other option is IPsec, the encapsulating or encapsulation, and you'll hear it both ways, I think, security payload. This is where we get encryption. Provides encryption, authentication, and integrity across the VPN. ESP and authenticating headers provide encryption and authentication. The authenticating headers, the AH, is the one that provides the authentication. Integrity, we're going to have that. The encryption down here, DES, 3DES or AES, What's the age of the device that we're connecting to? What's the age of the device that we're connecting from? What protocols are available on it? Because we can only use the ones that are there. The two devices, and part of the startup process is going to be the negotiating what protocols are we going to use. What's the most secure protocol that each of us, and then authentication, are we going to use an MD5 hash or a secure hashing algorithm? Diffie-Hellman can be used for key exchange, a number, and it can be used for encryption here also, is what this one is showing. Two different modes that we're going to have. We're going to have tunnel mode and transport mode. In the tunnel mode, the original header is not used. The tunnel mode is, I guess that generally, or not generally, but we can think of it as in a lot of cases, is going to be a site-to-site VPN. What's going to happen with it is we have our devices at each end, and we'll draw a nice tunnel here. And we have our 192.168.1.12 comes to the device. The entire data packet gets encrypted. And when it gets into the tunnel, it gets a new header, an unencrypted header. So it's going to have a new header here with an IP address readable by the multiple routers that it's going to encounter from us when we do these things. When it gets to the other end strips this header off, decrypts it, and sends it unencrypted on back to the private network, the protected network. You know, one of the things, and you say this and people say, oh, boy, that's dangerous. Only part of the connection is encrypted. And that's the important part to be encrypted, the part that goes across the internet. But everything on the backside that's on our private network is going to be unencrypted, typically going to be unencrypted. It doesn't have to be, but it can be. The transport model, maybe we'll think about going from device to device, that we would go across these things, and the only thing that we're going to encrypt or protect in this case is going to be the data portion of the this one is encrypted for the entire process. Every step of the way it's encrypted from one device. Depends on what kind of header we put on these things, whether it's tunnel or transport. How much of it is encrypted? Look at it. And this is the nice image of the headers that we have here. The original packet, we have the IP header, and then in transport mode, we have the authenticating header or the ESP header that gets put in after the IP header, the IP information. Transport mode, we're going to keep the original IP address. In tunnel mode down here, a new IP header. The authenticating header or the ESP header or the both header, we can use either or both, gets put at the back end, front end of the packet, so the entire data packet gets either encrypted or gets encapsulated. Then we need the new IP header with the unencrypted IP address so that it can get from one location to the other location. The types of VPNs, client to site VPNs, also known as remote access VPNs. That's what you're going to use on the Saturday morning in the second cup of coffee. Site-to-site VPNs, that's what a lot of organizations use, that from one to the other. We have an endpoint that establishes a VPN with another endpoint, tunneling mode to do these things. Host-to-host VPNs, the whole thing is going to be encrypted, or if we're using encryption for that. And then the dynamic multipoint VPN, which is kind of a neat thing. It's a hub and spoke, and that's one that we'll look at here in a couple of minutes just to see what it looks like. So the client to site remote access VPNs connects the client to the remote site, also known as remote access VPN. This is the one that we can use to get on our network. Something to remember when you have users connecting to your network via a VPN. When they get connected, they're on your network. If they have a virus, they're on your network. It's on your network. If they have a worm, it's on your network. If they have a a vulnerability that some smart guy has compromised, they're on your network. So when we do this, we're actually putting these devices on the network. The prior employer had a situation where they hired a developer who worked, and then they found out that the developer had so we're getting a little curious about the computer. Problem is, we already hired this person. Problem is, we can't make them do anything with their computer. We can't make them go out and buy an antivirus. We can't make them update it. It's their private device. The only thing that you can do in those circumstances, if you want to be able to maintain the consistency, is to provide you then own it. You can do whatever you want to with it. You can force it to be updated. You can put an antivirus on it. You can update the antivirus and all of those things. But when somebody connects to your network via a VPN, they're going to get an IP address on your network. They're on your network. It's the same as if they walked in and plugged the device into a switch that is there. Install and configure a VPN client. We need to do that, and I can get it here. I did this. I was trying to do some stuff on the DevNet network, the Cisco DevNet network, and you have to use the AnyConnect client for some of those things. I put too much into it. I have never been able, by the way, I've never been able to connect to any of the stuff there. I've not tried lately when you do that, but it says it's ready to connect. I would go in here or have them use a VM on their device. You still got to be able to have the protective devices on that. And the VM would still be their VM. I understand what you're saying there, but a VM can get infected just like a physical machine. If you're running virtual machines, they need to have the updates done on them. They need to have their own antivirus. They need to have their own firewall. They need to have all of the protections because it's a computer. All it's doing is sharing the hardware through the hyperterminal. So those things could be helpful to do that, or I guess we could send them a VM that we updated. But the VMs, when you do them, they need the same protections as the physical machine because all they are is just a different instance of the operating system running on the configured the VM, with their image and software. You can do that as long as, because then it's your image, you own that image, and you can have it configured to do all of the updating. You guys see that in the chat, the questions that he's asking in the comments. You can do that, but what you want to be able to do is to be able to be sure that the remote device is up to date. But we have it ready to connect here. We'd put an IP address or a name in here. And then we connect. This is on my wired network. There are other places I could connect it to because I have a wireless. I could go to the Spectrum 5G. I'm not going to do that because then it would try to shift and my connection would go away. So we're going to leave it on the wired network. And that kind of messed me up. It really messed me up. The wireless, the first one I put it on was a wireless. It's like, why won't this thing work? Why can't I go anywhere now? And I couldn't go anywhere now because I had the wrong network selected. There are some other things in here that can be configured on this also, but the Cisco AnyConnect, that client is free. If you need it and want it, you can download it. Install and configure the VPN client. We may use SSL, Secure Socket Layer, is a very convenient one because the port 443, the SSL port, is probably already open on your firewall. We can connect through that. The downside is when we do these things and if we allow connections through the firewall and it's encrypted, your firewall can't read any of that encryption. So people can actually, if you have one of these guys that's connected through the firewall, not to the firewall, but through the firewall, and they have a virus go through there, then you've got a virus getting encrypted, getting onto your network. But SSL, data is transferred between the browser and the server after authenticating the user. That's becoming a very popular way On the VPN server, ISACAMP has got to be enabled to enable the negotiation between the client and the server. There's going to be two phases, phase 1 and phase 2. And there is going to be, or there is in the share folder, a VPN packet tracer lab. I wish you'd do it so that you can see how these things get configured one to the other, and then how the different phases work. We create a phase 1, creates a tunnel to protect the authentication and the data tunnel creation. So what we're going to do is create a tunnel, an encrypted tunnel, to negotiate in. And then phase 2 is going to create the tunnel that protects the data. So we're going to have two tunnels created in this process. One, the tunnel to protect the data, to protect the negotiation of the tunnel protocols, and then a tunnel to protect the data that we have with these things. The remote PC uses the VPN client to authenticate to the server. After authentication, HTTP messages are allowed to pass through the SSL VPN client. And we kind of jumped around. We used the Cisco AnyConnect. That's not necessarily an SSL, but we may have an SSL, secure socket layer client, that allows these things to happen. It doesn't really matter. Well, I guess it does matter, depending on what matters on what's configured on each end. But SSL, secure socket layer, is going to be a protocol that's going to make these things secure. All the packets are sent to the other end of the tunnel are going to be encrypted with the whatever protocol we select. The site-to-site VPN is what businesses would use. Maybe what a LeaderQuest would use to create a site-to-site VPN between Denver and Colorado Springs, between Denver and Dallas, between Denver and Jacksonville. ECPI Technical College, ECPI University, used a concept that everybody connected to the headquarters activity. So had a VPN tunnel to each of the locations. Why did they need that? Because the headquarters activity centrally stored all the PII, the personally identifiable information, and you want to protect it as it's being transmitted from one to the other. They actually kind of went a little bit overboard. We had leased lines, and within the leased lines we had a VPN. So kind of a double protection there. A leased line is a private network, and then encrypt the data going. IPsec defines one of the rules for creating the site-to-site VPNs. Architecture or framework for the devices, and it defines how the devices will achieve the confidentiality, integrity, and authentication. And this is another thing that you would see if you will go ahead and do that VPN lab, that we're using a suite of encryption protocols, not just a single one, because all the devices may not be able to do that. We want to use the most secure that's available at both ends of these things. The following 4 steps: the sender provides the original data packet, and the session key is encrypted with the receiver's public key, kind of like what we talked about earlier. And then the receiver will use his private key to decrypt this thing. So the sender is going to create a session key, and then we'll encrypt it with the public key of the other guy, of the receiver. Public key anybody can have. Public key is public. The receiver then will decrypt the session key with the private key. The reason we want to do this is symmetric keys, session keys, same key at both sides, is going to be a whole lot more efficient than trying to do any of this stuff with the individual public key and private key. So what we do is use the asymmetric public key, private key in order to get the symmetric key shared to both ends of the conversation. The sending device encapsulates the encrypted data into the packet. That includes the new IP and VPN headers, and then the sending device sends the new packet to the destination VPN. Receiving VPN will use the decrypted session to decrypt host-to-host VPNs, computer-to-computer, a host at one location to a host in another location through a VPN tunnel. Again, an encrypted conversation, an encrypted connection for these things. The difference between them and the site-to-site, the entire data chain, the entire conversation in this case is going to be encrypted with these things. Only the resources on the remote host are able to are available to the remote. Only resources on the remote host are available to the remote host. The organization, partners, payroll, outsourcing. There are a number of things. Maybe you want to get a direct connection to a server, for instance, that you can manage. The dynamic multi-point VPN is and this is the one I said we go back to. So let's see if we can go back to. You notice that it's centering everything this afternoon. When I do this, I have if I can get it where I want it. I have a hub and spoke arrangement for this thing. I have a hub, and it's this guy up here. If I go into the console, and it's going to take it let's see if we can make it a little bigger. If I show DMVPN, dynamic multipoint VPN, it says that it has, the state is up, it has a connection to 10.1.1.2 and 10.1.1.3. It's the hub, it's connected to the other two sites. What we want to be able to do with this configuration, and we'll make it bigger, but what we want to be able to do is to do a direct VPN from one to the other without having to go through all of this setup. And I've done the show here, and let's try the show here. Show dynamic multipoint VPN. It goes to the 10.1.1, the 11.1.1, the tunnel devices, the physical connectivity. It does not have a connection over here to the 10.1.1.3. And I always forget which one to ping in order to make it come up. So let's try to show the dynamic multipoint VPN. So it's going to be and what that would do, I hope anyway, is to now cause a connection. It's up. This one is up. It says I haven't done anything with it. We have now dynamically created a VPN through the cloud without having to go through the headquarters activity, the spoke in the hub and spoke. This uses the NHRP protocol, which is the Next Hop Registration Protocol, I think is what it stands for. We can look at real quick here some of the configuration that goes on with this one. Let me go fast. But we have to have a tunnel interface. The bandwidth gets specified. The IP address. The MTU, which is normally 1500, gets reduced in size to take into account the maximum transmission unit, the extra header information that goes on with this thing. IP, NHRP, map, multicast to 10.1.1. We're going to register our IP address with the spoke, and the other guy is going to get that information from the spoke. No IP split horizon. We have to turn off split horizon. Remember, it is a physical interface configuration, the split horizon is, so that there are times if we have multiple comes in and multiple comes out, that we need to turn the split horizon off. Solves the administrative issues for setting up multiple VPN tunnels. Blue Ridge, we had a VPN concentrator, which actually made it a whole lot easier than trying to go into the multiple individual devices to do these things. Can combine technologies. The generic routing encapsulation tunnels do just that. They are an encapsulation tunnel. They're not going to do encryption. We have to add IPsec or whatever we're going to use to the protocols. Of course, IPsec, we're going to add the protocols to it that we're going to use. IPsec encryption would be used here. And then the next hop resolution protocol, I said registration, resolution protocol. We do have to register with the hub, and the hub is where the addresses will be resolved from. The spokes have dynamic permanent GRE IPsec tunnels to the hub, but not to the other spokes. And then the two configurations are going to be hub to spoke and spoke to spoke. Then that's exactly what we had on the one that I showed you. The spokes have a dynamic. When we did the show on the each of them on the hub, it was connected to both. We looked at the spoke before we tried to send traffic to the other hub and spoke. Well, the other spoke, the hub to the spoke to the other spoke device or end device. It only had connection to the hub to the central location, and then after we did the connection, we were going directly to it. Not internal routing protocols, OSPF and EIGRP, are going to be used across the tunnel. The dynamic, and this is just an image of what it is. We looked at what it does. That we had the configurations there, the registration, and all of the other activities that take place when we do those things. You would go to the individuals, the spoke A would go to the hub to get the address of spoke B, and then it would then create the tunnel between the two so that we didn't have to go through the hub. I talk about that. In case the hub goes down, you can still create these things, but you still got to go to the hub to get the addressing information. After this, we got some troubleshooting things, and I think what we're going to do is let's go ahead and take a break right